Before we get started with SN1, let me give you a kind of a short summary of all the different things that we discussed about the SN2 mechanism. So first of all, the kinetics. Well, the kinetics, we know that the rate of the reaction should be proportional to the concentration of both the substrate, that is the alkyl halide that is reacting, and the nucleophile. So that means that if I double the concentration of the substrate and double the concentration of the nucleophile, the rate of the reaction will be 4 times the one that we observe with the normal amount of those substrate and nucleophile. Or if I triple the concentration of the substrate and double the concentration of the nucleophile, so then the rate of the reaction will be times 6. All right, so there we have kinetics. How about the energy diagram? Energy diagram, well, I would expect that the energy diagram will be kind of a boring looking diagram, just a transition state, and there is no intermediate, How about the mechanism of the reaction? Well, the mechanism, we can write down a mechanism, rather simple. You will have your carbon atom with the 3 substituents there. You will have the nucleophile having a backside attack, and then the leaving group will depart from this side, half the way of the reaction. You will have the nucleophile will be partially attached. The leaving group will be partially broken bond there, and then the 3 other groups will be in a trigonal planar arrangement, right? It's like the inversion of an umbrella. And then when you finish the reaction, then now the nucleophile is completely attached, and then the 3 other groups are pointing in the opposite direction, right? And the leaving group is completely detached. So that's why we say in this reaction there is an inversion of the configuration, right? So we have inversion of the configuration. So that is the mechanism. So we have the energy diagram. Energy diagram is done. Having some technical issues here with the pen. Let me try to pause the recording. We resume the recording, okay? So we said the energy diagram, we did that. The mechanism, we did that as well. Stereochemistry, we said you have inversion of the configuration. Because if you start, for instance, with a group A, B, C, and you have the leaving group here, then the product that you will obtain will look like this. You will have the nucleophile attached from the opposite side, and then you will have your A, B, and C over there. And that means that if the stereochemistry of the starting material was S, then the stereochemistry of the final product will be R. So that is going to be quite distinctive. And then we discussed the individual, the effect of the nucleophile, leaving group, and substrate and solvent. So what kind of nucleophile will be better? Always we prefer a nucleophile that will be negatively charged if possible. That will make it more effective. As far as the leaving group, we prefer leaving groups that will be better leaving groups. For instance, you can have tosylate or the halogens. Those, they tend to be very good leaving groups. Bad leaving groups will be things like fluorine or OH. How about the substrate? Well, the substrate, you may have different types of substrate. You may have a a methyl halide, or you can have a secondary or tertiary. So we prefer alkyl halides with small groups attached to the carbon, because in that way the approach from the backside will be easier. And if you have bulky groups here, let's say you have terbidyl groups here, 3 terbidyl groups, the approach from the backside will be virtually impossible, right? So that's why you could expect that the reaction will be very, very slow in this case. And as far as the solvent, so you would prefer solvents for an SN2, you will prefer solvents that are polar but non-protic. So solvents that will be ideal for that will be HMPA, hexamethylphosphoramide, that is what HMPA stands for, or you may want to have a DMF, dimethylformamide, or dimethyl sulfoxide. All of those are pretty good solvents. Bad solvents will be protic solvents that can form hydrogen bonding. Why? Because if you have formation of hydrogen bonding between the solvent and the nucleophile, then the nucleophile will be just way too stable, and it will be surrounded by solvent, a solvent coordination sphere, right? And so on, then it will not be very effective to attack the substrate. All right, so with that now we can get started with the SN1 reaction. So SN1, the mechanism of the SN1 reaction is substantially different. In the SN1 mechanism, we have first departure of the leaving group, and then later on, the nucleophile will come and get attached to the substrate. So many of the different aspects will be a complete reversal of what we saw in the SN2. For instance, while in the SN2 having a tertiary halide was bad news because the backside attack was very difficult, in the SN1 reaction, a tertiary halide will be a good thing to have. Why? Well, because if you have breakage of the carbon-hydrogen bond first, that means that when you have that breakage, for instance, if you have 3 methyl groups here, 3 methyl groups, and then graciously the bromine decides to go, so what you will form will be a planar, it will be a trigonal planar carbocation with 3 methyl groups. Because you have 3 methyl groups, tertiary carbocation, that is good news. It's fairly stable, right? So, and then later on, the nucleophile will come. The nucleophile will come, let's say that is a negatively charged nucleophile, and the attack can be from one phase or from the other phase. So you can already guess what is going to happen with the stereochemistry of a reaction like this. That means that if you start with a compound that is chiral, let's say that all the 3 substituents that you have around the positively charged carbon, all the 3 groups are different. Well, so then the starting material is chiral, and then because you will have attack from one side or the other, you will end up with a racemic mixture, right? And then we said in the case of the SN2 reaction, the use of a methyl halide, that was a very welcome thing, because the approach from the backside was very easy. Well, you bet, in the SN1, that is going to be bad news. Why? Well, because if the bromine leaves here, what is going to generate? It will generate a carbon with 3 hydrogens, so that will be a methyl carbocation. And you know that methyl carbocations are not any stable, right? So that's why the reaction will go so extra slow with a methyl alone, right? Just a methyl system. A methyl halide will be very unreactive. But a tertiary halide, there you can see, is more than 1,000,000 times more reactive than the methyl halide. And so how about the energy diagram? Well, the energy diagram also will be different because you will have first, you will go through a transition state, you will form a carbocation intermediate. So we have here formation of an intermediate, and then we go downhill from here, and then you form the final product. But here there is formation of an intermediate, and that intermediate is a carbocation. All right, so I think I may stop here, and then we continue in the next installment.